Let's start our M seminar, and today we're happy to have Christopher Beem from Oxford University. He will speak about graded unitarity. Chris, please. Oh,
Great. Thank
now I
you.
see it.
Yeah, for the invitation. I'm very happy to be joining you all virtually. Oh, no, now it tells me my sharing is paused. Okay, bear with me for a moment.
Don't worry. Yeah.
So I'll try it this way. So thanks everyone, and thanks for bearing with me as I tried to get this working. So I'm going to be talking about some work that's been going on for a few years now that so far has appeared in three publications, a couple of preprints and one has been published. Um, Originally, a paper with Arash Ardahali, Maddalena Lemos, and Leonardo Rastelli, which is very much a sort of physics paper on the subject. The second paper listed by Nicholas Garner and myself is more mathematically careful, and it's going to be probably what I say the most about today. And then I also have some ongoing work with my student Harshal Kulkarni, which is again somewhat more physicsy in style. And so my plan today is to start out, I think, pretty briefly with some motivation of the subject coming from supersymmetric quantum field theory in 3 and 4 dimensions. But then to spend most of the time talking about the definition and sort of properties of this, we think, interesting novel structure on vertex algebras that we've called graded unitarity. I'll give some very simple examples of the so-called symplectic boson and symplectic fermion, which is what SB and SF mean here, which will then help discuss where most of the, I think, interesting technical results so far are, which has to do with the behavior of, or the consequences of this structure for certain semi-infinite cohomology problems or BRST cohomology problems for vertex algebras. And at the end, probably very briefly, I'll mention some very conditional classification type of results, but I'll already mention here that it's not really a satisfactory set of results, and they involve quite a bit of upfront assumptions that we'd like to be able to relax, but at the moment, don't know how to. Okay, so the motivation for this whole story comes from some observations that I guess go back more than 10 years now. Um, that interesting vertex algebras, interesting for various reasons, uh, seem to arise in a variety of ways coming from higher dimensional supersymmetric quantum field theories. Higher dimensional here means more than 2 dimensions, where vertex algebras in physics are normally thought of as being associated with 2-dimensional conformal field theories. And the two sort of most dominant paradigms in this direction are some work of mine from 13 years ago with Lemos, Liando, Pilares, Rastelli, and Van Rees that extracts a vertex operator algebra from any given 4-dimensional n equals 2 superconformal field theory, whatever such a thing is. Physicists have a lot of opinions about the sort of world of such gadgets, but they're very physicsy. And then there's slightly more recent work going back to a paper by Kevin Costello and Davide Gaiotto from 2018 about associating certain vertex algebras to 3-dimensional supersymmetric quantum field theories where there's some
Chris,
extra
sorry
data.
yeah,
Yeah.
sorry for interrupt. When you say vertex operator algebras, you mean not just the chiral part, but the full thing, the full kind of like
No, I
even in
mean,
two dimensions, you have chiral thing, which is mathematically well understood, and the whole thing with unitarity when you combine chiral and anti-chiral sectors. So just to keep in mind, it's VOA, it's for full theory or just for some
no,
sector
just
of
I
the,
mean just the chiral part. These are just the chiral
just the
parts.
chiral.
So these are
Okay.
um, these gadgets that are under quite a bit better control mathematically, but the I mean they
Yeah.
can still get quite complicated, and the theory of them when you move beyond sort of rational or say pseudo cofinite various adjectives that you can attach to them, it can get pretty complicated.
Okay. Okay.
So so just as as an aside, I'll mention that the vertex algebras that come up in both of these settings, most of the time, for some reasonable notion of most, don't have any of the nicest properties that representation theorists have used to get really good control over classes of vertex algebras. So they're usually not rational and they're usually not C2 cofinite if you're familiar with that property. Although sometimes they are for special cases. So so the sort of driving force in a variety of works has been that the vertex algebras that come in this way, come into one's life in this way, often come with a variety of special properties that are somehow very natural from the point of view of higher dimensional supersymmetric quantum field theory, if you're sort of indoctrinated in the way that people think about those things. But sometimes they look quite novel or not obvious, just as vertex algebraic properties. And I think it's fair to say that there's still quite a bit of effort going into some sort of fairly undirected effort to try to sort of characterize the sorts of algebras that are relevant from these points of view. And today I'm going to be focusing on one property in particular, which is related to the fact that the four-dimensional so I hear what for 4D VOA. So vertex algebras that arise via this sort of construction from four-dimensional quantum field theories. The underlying four-dimensional theory is supposed to be unitary in some sense, in the sort of usual, say, axiomatic sense of unitary quantum field theory. But the vertex algebras that arise normally are not unitary vertex operator algebras in the usual sense. And so instead there's some sort of shadow of higher dimensional unitarity that shows up that we've dubbed graded unitarity. And it's not a very obvious definition, but once you're working with it, it has some nice consequences. Okay, I'm now going to just sort of dive into some of the construction. So it's going to need some definitions um, that I'll just assert. So so on a vertex algebra, going back to work of Haisheng Li, I should have written down the citation, Haisheng Li from I think 2004. There's some notion of a good increasing filtration on a vertex algebra, which is in the first instance just some increasing exhaustive filtration by subspaces. But with the important property, the first one here is not very interesting. It's the vacuum vector that I'll always call zero in sort of a ket notation, is in the zeroth layer of this filtration. But more importantly, there's some condition that if you take a vector in the pth layer and a vector in the qth layer, and you look at their OPE, alternatively, if you look at the sort of nth product that you get from acting on y with x under the vertex operation, then, okay, here I had meant to do some annotation that I can't do right now, so you'll hopefully bear with me as I say it out loud. So using the standard conventions, the negative modes, so the negative nth products correspond to the regular terms in the OPE of x with y, and the zeroth and positive modes correspond to the singular terms. And so the condition on a good filtration is that uh, under the nth product, the filtration degrees add in the obvious way. But if you look at the singular terms, the ones that are responsible for the sort of interesting non-commutativity of the vertex algebra, um, they always land in one lower layer of the filtration. And a reason that that's a good property that was identified back 20 years ago um, is that if you have a good filtration on a vertex algebra and you take the associated graded, um, then you'll get something which has a commutative algebra structure but retains a little bit of the non-commutativity in the form of a so-called Poisson vertex algebra structure.
Uh,
So this is a sort of semi-classical version of a vertex algebra.
So maybe you will talk about that later, but you mentioned this 3D n equal 4 story. And if you construct whatever the filtration, which probably you'll explain later,
Yeah.
so is the associated graded somehow related to Coulomb or Higgs branch of the corresponding theory?
Yeah, that's a great question. So actually, um, maybe I should sort of give this sort of disclaimer for the rest of the talk. The things that I say and that I write are really going to be exactly true for the case of these vertex algebras coming from four-dimensional theories. And for the ones that come from three-dimensional theories, there's a slight weakening of a lot of the constructions I'm going to describe that we called weak graded unitarity in the paper with Nick. Um, and and many of the results have an analog in the weak setting. But in the weak setting, you don't necessarily have a good filtration. Um, you have a filtration that isn't exactly good, meaning that there isn't an there from a four-dimensional point of view, um, you don't have a you don't or sorry, I should say from a three-dimensional point of view, you don't have a natural commutative limit of these vertex algebras. In the four-dimensional
Mm,
case,
okay.
in the four-dimensional case, the thing that you get in this associated graded looks like something pretty close to, but not exactly the same as the like functions on the infinite jet scheme of the Higgs branch. So I'm going to have a sentence that appears later in the slides, but um, jet schemes of Poisson varieties are a place to get Poisson vertex algebras. And
Yeah.
so when you are getting these sorts of semi-classical limits, it's natural to ask whether there's some Poisson variety out there where you're seeing something like its jet scheme. And the answer in the four-dimensional case is sort of. You're getting something that looks close to a jet scheme of the Higgs branch, but it's not exactly true.
Okay. All right.
Um, right. So for one of but just to reiterate the conclusion for one of these good filtrations, there's a natural semi-classical limit that you get by taking the associated graded, which will then be a Poisson vertex algebra, where if you're keeping track of these things, the it's z graded and the degree of the lambda bracket, the thing that sort of sees some of the non-commutativity of the vertex algebra is -1. Now, there's some slight refinement of this, which isn't super interesting, but technically it's what you have to do in the cases that come from 4D, which is to introduce something that we called a half integral good filtration, which is something that you can define when you have a Z2 graded vertex algebra around. So when I have such a thing, I'll always call sort of the Z2 invariant part V0 and the part on which Z2 acts by -1 as V1 half. And then the relevant thing is to have one of these increasing exhaustive filtrations separately on the even and Z2 even and odd parts, which is encoded in in this line with these alphas taking values 0 or 1/2. Um, but now the goodness condition sees a little bit of that Z2 grading. Um, and so in particular, if you have X in the P plus alpha layer, where alpha again is 0 or 1/2, and Y is in the Q plus beta, um, then in addition to seeing P plus Q adding, alpha plus beta add as well in the filtration. So I think unless you're way faster than me, like you're not going to probably stare at this and have it make a lot of sense. But I claim um, it's the natural generalization of this good filtration condition to the case when you want there to be some extra Z2 grading that is somehow sort of measuring the half integrality of the underlying filtration.
Is it specific for 4D or for any, like for
No,
2D super?
this is relevant for three dimensions as well. Um,
What about 2 dimensions?
in
Uh,
in two dimensions, I don't know I don't yet know of a situation where any of what I'm saying today is sort of shows up as relevant, but
mm,
but
okay.
that's just my own ignorance. Um, okay, and just for future reference, this thing that measures the Z2 component that's going to be 1 in on V0 and -1 on V1/2, I'll call S. That will show up later. Um, and then if you have this slightly refined structure, then you're in the semi-classical limit, you're going to get a half integer graded Poisson vertex algebra, again with Poisson bracket of degree -1. Of course, you could just rescale your grading if you wanted to, and say that this is a Z-graded Poisson vertex algebra with bracket having degree -2. And here's the comment that I sort of already said. So this kind of structure, in very general terms, is something that you find on infinite jet schemes for really for Poisson varieties, although somehow the things that come up in these three-dimensional, four-dimensional constructions more often look like they're jet schemes of some holomorphic symplectic variety or scheme. And there's I think there's a lot of interesting questions about the degree to which uh, these vertex algebras do or don't end up um, being some sort of like deformation quantizations of jet schemes. But I won't have anything specific to say about it today. Okay. Um, from now on, I'm going to be making an assumption. This is always true in the things coming from higher dimensional supersymmetric quantum field theory. Um, uh, but in principle, you could consider vertex algebras that don't have this property. We'll consider vertex operator algebras that are of strong CFT type, meaning they have a conformal grading by non-negative half integers. The only thing with conformal weight 0 is the vacuum vector. And this is a very technical condition. The L1 uh, component of the Virasoro algebra acts on the conformal weight 1 space as 0. And that has the technical consequence that you get a unique up to rescaling invariant bilinear form, bilinear pairing on your vertex algebra, where the notion of invariance is some technical condition that's reasonable but doesn't look very beautiful to look at it when it's written out. This formula that appears here is an Eiffel if you don't usually look at these things, but it's the natural generalization of saying that you get a pairing on quasi-primaries coming from two-point functions, where you just measure the coefficient of the two-point function up to some formal phase factor, and then all of the extra stuff in this big formula comes from making things work correctly on SL2 descendants, on sort of derivatives of things that are derivatives of other operators.
So it's not symmetric.
it has a
This
symmetry property, but it's a slightly complicated one. So essentially you need to think about it as it's morally speaking like a pairing between an operator that you put at zero on the Riemann sphere and an operator that you put at infinity. So the invariance condition. Oh, sorry, maybe that's not what you're asking. This pairing this pairing in a up to signs is symmetric. It has definite symmetry properties that are determined entirely by the conformal weights of x and y and the by the conformal weights of x and y and the Grassmann parity of them. But this isn't going to be the form that we actually want. We'll build a slightly better thing in a moment. But this is a thing that you always have, and it's morally speaking taking coefficients of two-point functions in a way which is slightly improved so that it works well with the full vertex algebra structure. And then coming back to filtrations, when you have this bilinear pairing, we'll call a filtration non-degenerate if the restriction of the pairing to each component of the filtration is non-degenerate. And then an important fact is that if you have one of these non-degenerate good filtrations on a vertex algebra, then you can turn it into an actual grading just by sort of doing a Gram-Schmidt or orthogonalization of each smaller component inside of the next. That's not going to be a grading on the vertex algebra in the sense of a graded vertex algebra, in the sense that the grading is preserved by the nth products. It's a grading on the underlying vector space, which will only be preserved in the sense of a filtration. So the filtered components will come from adding up all of the graded components with grade less than or equal to the filtration degree. And so when you have this, when you have one of these half integral good filtrations, then we'll define something that measures the grading. So after you refine to the grading, we'll have something that measures the grading mod 4. So this sigma map is the square root of minus 1 I to the 2p. So 2p is an integer. And so this is going to sort of be a refinement of the Z2 grading that we had by assumption into a Z4 decomposition. Okay. Now we'll define a conjugation on a filtered vertex algebra like so. So a conjugation is some map of the underlying vector space that sends the vacuum to itself, that commutes with the translation operator that I've called del, and that is pretty close to being sort of a vertex algebra automorphism, except for some Grassmann parity factor. So here, x and y inside of vertical bars is their Grassmann parity. So you get an extra minus sign for fermionic operators. And this is C antilinear. For your vertex algebra is defined over C. And we'll say that a vertex algebra equipped with a non-degenerate good filtration and a conjugation has a quaternionic structure if this conjugation squares to the Z2 grading, as does this sigma operation that we were able to define after refining the filtration to a grading. And additionally, rho and sigma commute like so. And here omega is the Virasoro vector. So the Virasoro vector should be preserved by the conjugation. So this definition is really a direct generalization or sort of analogy extension of a definition given by Ettingoff and Stryker in 2020 in their treatment of the sort of deformation quantizations of symplectic singularities that arises from another thing you can do with three-dimensional n equals 4 superconformal field theories.
Is it something they called short star product or something like
Yes,
that?
exactly,
Yeah,
exactly. So,
yeah.
so this will we will eventually have a shortness condition as well. Um, and in both cases, I forget exactly when I wrote this down. It might be later in the slides. In both cases, um, there's a secret, which is that underlying these, when these things are coming out of physics, underlying um, everything is some SU2 action of which this grading that we're seeing, this filtration that turns into a grading, is secretly measuring the action of the carton of an SU2, which is sort of a hyperkähler SU2. So in the symplectic singularities, oftentimes your space is secretly hyperkähler, but you're only studying it in some complex structure. Um, and these sort of extra conjugation ingredients um, are sort of a residue of the extra hyperkähler structure. And morally speaking, I would say the same thing here, except that it's not so clean in the sense that we don't start out with just some symplectic singularity that you could either know that it is or isn't actually hyperkähler. Um, it's more in the sense that in the physics there's some SU2 action around which somewhere else looks like a hyperkähler SU2. I'll say a little bit more about this in a moment, but not a lot. Um, so with all of these extra ingredients, you can define an improved version of the bilinear pairing that uses both this sigma action that was this Z4 refinement of the Z2 grading, and also the conjugation row. And you can show pretty easily that this thing will be Hermitian. And if the original form was non-degenerate, then this thing will be non-degenerate. So you get some non-degenerate Hermitian form on the underlying vector space of the vertex algebra. With respect to this Hermitian form, some things are a little bit complicated. So, for example, and I haven't written down the version of this that would hold for a conventional unitary vertex algebra, but defining the adjoint operator of one of the nth product operators of some, say, quasi-primary of weight h, um, now involves all of this extra information. So there's sort of extra phases and extra automorphisms that show up in the definition of the adjoint. And then finally, with all of that machinery, the condition that the vertex algebra with these extra structures is graded unitary is just the statement that this Hermitian form is positive definite. And something that you get fairly immediately that we proved in the paper with Nick, and this is the analog of what you were mentioning, Jan, for these deformation quantization problems, is that if you have a state that has, say, conformal weight h, and after refining the filtration to a grading has grade p, then you can look at the nth product, you can look at its decomposition into homogeneous pieces. So now you can ask, if I look at the nth product acting on a state which has grade q, what are the restrictions of those maps um, to the different components of the image, the different sort of grade pieces you can land in, and you get a truncation condition. So in general, the goodness condition of the filtration would mean that the things that appear on the right-hand side would have grades anywhere less than or equal to q plus p. So here we have a sum over p prime less than or equal to p of q plus p prime. But this graded unitarity property allows you to prove that the modes that decrease the grade by more than p will vanish. So that's exactly, if you forget about the lowercase n's and you forget about the first subscript under these V's, which is this sort of extra conformal weight creating that's around in the vertex algebra setting. This is precisely the sort of truncation condition that shows up in these short star products on symplectic singularities. And here's this comment I was saying before, and there's nothing really more interesting here, which is to say that physically, this additional grading that we sort of accessed via the non-degenerate filtration arises from there being an SU2 symmetry of the four-dimensional theory, and all of these vertex algebra operations are some shadows of a more elaborate sort of operator product structure in the full four-dimensional theory, where you're, amongst other things, taking a product of operators that live in spin P and spin Q representations of some internal SU2 symmetry, and so they're going to obey the usual selection rules on the addition of angular momentum between spin P and spin Q. Um, this is less exciting, but there's a graded unitary version of the spin statistics theorem that tells you that the Grassmann parity of an operator is determined by its conformal weight as well as its grade with respect to this extra gradation. In the usual unitary vertex algebra setting, there would be no P here, and you would have a spin statistics theorem that said that the Grassmann parity was given by twice the conformal weight. So you're able to break the usual spin statistics relation by introducing this extra grading away from zero. Okay, so that's the main definition and a couple of very simple consequences. Uh, I'm going to mention a couple of examples that are very easy once you've sort of processed all of the definitions. Nothing sophisticated is happening, but they were still important to work out. And they're the symplectic boson and the symplectic fermion. So a symplectic boson is built starting with a symplectic vector space over C. I think I've overloaded omega in this talk. Now omega is a symplectic form. And we'll choose a basis for the vector space such that the symplectic form takes the form of a unitary matrix. You can always, I mean, you could choose Darboux coordinates, slightly less specific as to make this choice. You don't have to make this choice, but then the formulas get worse if you don't make it. And then the symplectic boson, which is sometimes called the beta gamma system in the physics literature, is generated by dimension of your vector space many fields of weight 1/2 with a simple free field OPE, which is controlled by the symplectic form, as appears here in blue, which amounts to a quite a simple mode algebra on the nth and mth products, which is written below. So the symplectic boson is not a unitary vertex algebra, but it can be given a graded unitary structure. And to do that, you define this filtration. So the P over tooth layer of the filtration will just be things that you can write by, okay, so this is in sort of mode language. Alternatively, you can think in terms of normally ordered products, nested normally ordered products of the Qs. And it's just things that you can write with at most P of the generating fields. And the conjugation is up to some conventional phases encoded in the symplectic form. And one of the cute things about this whole structure that you can see here is that now when you run through this machinery of defining the Hermitian form that I had before, and you define the adjoint of these modes, then unlike what would happen in a conventional unitary vertex algebra, or in some attempt to make a vertex algebra look unitary, the rules for taking adjoints of modes have extra signs depending on which mode number you're looking at. So if you were trying to make this thing look unitary using the usual definitions, you wouldn't be allowed to include an extra sign in the action of the sort of star operation taking adjoints. depending on whether you're looking at a positive mode or a negative mode. And that actually rescues positivity completely. So another way to invent this whole story would have been just to um, start making up rules in order to make something like the symplectic boson actually have a positive definite inner product. You'd have to change the inner product in some funny way that would start knowing about how many Qs you had. And it's not hard to check by just some explicit calculation that with these extra signs, um, the Hermitian form that you get is positive definite. There's an almost identical story for what's called the symplectic fermion vertex algebra, which is again defined by a symplectic vector space, where essentially all of the formulas that appear here are the same, except now the generating fields that I've called eta have conformal weight 1 and they're Grassmann odd. And the formulas look close, but not identical for the symplectic boson. And the graded unitary structure is going to proceed in almost the same way. So you can define the filtration just by counting the number of etas that you're acting on the vacuum with. The conjugation is defined in terms of the symplectic form. And again, you get this funny extra sign in the adjoint that rescues positivity. And again, the symplectic fermion is not a vertex algebra that can be made unitary in the usual sense. But you're
Are they
given access to these extra
somehow
signs.
causal dual of these two stories, boson and
I
fermion?
don't, uh, I'm afraid I'm not a person who can use the words causal
Uh, uh,
dual with any
okay,
confidence.
okay, okay, okay. Then I
Um,
take them back. You're
it
right.
sounds like the sort of thing that I might have heard people say, but um, I don't I don't think in some like really direct way. Okay. And again, you can do some calculation by hand to see that this thing is graded unitary, that the Hermitian form is positive definite. And this now gives us the setup to study the main application so far, um, which is in the world of so-called semi-infinite or BRST cohomology. So I'll give a very brief review of a construction here, um, which goes back to sort of string theory, but also shows up naturally in these higher dimensional quantum field theory settings. So we'll have capital G, a compact semi-simple group with a corresponding Lie algebra, lowercase g, c, and a basis uh, with structure constants and a killing form. And we will say that a vertex algebra that I'm now going to call V sub mat for matter, because this goes back to in the higher dimensional setting, this is like the part of the vertex algebra that comes from the matter and not the gauge fields. So we'll imagine that we'll have a G action on our vertex algebra in the sense that there's some vertex algebra homomorphism from the affine current algebra at level minus twice the dual Coxeter number into my vertex algebra. So more prosaically, this means that in the vertex algebra V map, there's some subalgebra that looks like an affine Kac-Moody vertex algebra at level minus two times the dual Coxeter number. It's important that it be at that level for the following to work. You can then define what's called the relative BRST complex, which just comes from taking your original vertex algebra, tensoring the symplectic fermion vertex algebra that you get associated to the symplectic vector space, which is just C2 with its standard symplectic structure, tensor the complexified Lie algebra. And you take the global G invariant parts of this whole thing. So you have a big G action on the symplectic fermion vertex algebra that integrates the sort of the lowercase g action and also on this matter part. It's a fun fact that this symplectic fermion vertex algebra has an outer SL2 or an outer USP2 automorphism that commutes with that GC action that you're taking the invariant subspace with respect to. And then there's some differentials that you can define that I've written out here. In many places in the literature, they're written a little bit differently. You can embed the symplectic fermion vertex algebra in a so-called BC ghost system, in which case you write this out a little bit more easily. But the BC ghost system doesn't have this outer automorphism symmetry, and it has an extra mode that you need to get rid of. So when you write it this way, there's actually a full sort of standard representation of USP2's worth of differentials. And you choose one, and the relative semi-infinite cohomology, which is usually written with these symbols on the right with a dot plus infinity over 2, that was defined by Voronov, but building on, no, sorry, built, not defined by Voronov, studied by Voronov, defined previously, but really coming from physics and from string theory, is just the cohomology of your this V vertex algebra with respect to one of these differentials. It doesn't matter which you take because they're all related by an outer automorphism. And this construction is fairly complicated, and studying these semi-infinite cohomologies, these BRST cohomologies, can be challenging. But this is the thing that you are instructed to do from 3 and 4-dimensional physics. I've written here in the 4-dimensional case. It's what you're instructed to do if you have a gauge theory. So if your higher dimensional theory is defined in terms of some semi-simple or reductive group acting on some matter, some space of matter fields that you have to define appropriately, then by the time you pass to these vertex algebra constructions, you end up with these semi-infinite cohomology operations. And the condition on the level of the moment map being minus 2h check then corresponds directly to the condition in 4 dimensions for the theory to be superconformally invariant. So there's some sort of matching of conditions there. I should have said that condition is required in order for the things that I wrote here as q plus or minus to actually be differentials. In order for them to square to 0, you need that precise numerical condition on the level of the Cass-Moody currents. Okay. So now suppose that the vertex algebra that you're putting into this machinery is graded unitary. We'll have one extra meaningful condition. Well, really two, but only the first one is very interesting, which is that we'll call this sort of chiral moment map, so this sort of Cass-Moody action on the matter vertex algebra good if the generating currents of the Cass-Moody vertex algebra are in the first filtered piece with respect to this non-degenerate filtration. So after refining to a grading, that means that they can have pieces which have grade 0 and they can have pieces which have grade 1. And then if they live in this F1 piece, then you can look at the actual nth products, the nth modes of these things, and decompose them into their homogeneous pieces with respect to the extra grading. And by the shortening condition we had before, they're going to be a sum of 3 pieces with grade +1, 0, and -1. And it turns out that for the non-negative modes, the things with degree +1 have to vanish just by the goodness condition of the filtration. And then for n non-positive, the ones with degree -1 have to vanish because they're the adjoints of the things with with grade +1. That's a bit of a technical point. The payoff from this technical point is that then when you look at the decomposition of the BRST differentials with respect to this extra grading, they end up only having 2 pieces. So you end up with your differentials decomposing into a grade +1/2 piece and a grade -1/2 piece. And then you can you everything is very explicit because we had everything in terms of these symplectic fermions and then these J's that we've now understood a bit. And so you can start computing what the adjoint what the adjoints of these various operators are and what their commutation relations are, and you get what's shown on the screen now. So the pieces with charge plus one are adjoints of pieces with charge, sorry, plus one half are adjoints of pieces with charge minus one half up to some signs. And defining some barred operators as these adjoints of the full differentials, you get a collection of operators acting on your vertex algebra, which have exactly the same algebraic structure as the algebra of differential operators on PQ forms on a compact Kähler manifold, with their same adjointness properties. So you actually get the full sort of consequence of Hodge theory, or most of the consequences of Hodge theory, uh, on these complexes of vertex algebras. In particular, you get a Hodge decomposition that tells you that your vertex algebra decomposes as the kernel of a Laplace type operator that you get from the anti-commutator of Qs and Q bars, and images and kernels of the Qs. Sorry,
Is the
I don't know
form
why there's a
is
superscript
the for,
subscript change here. They should be
yeah,
the same.
you mentioned formality at the beginning of your talk. Is it
Yes.
also kind of similar to the one which one has for
Yeah,
Keller?
that's going to be in 2 pages, I think. So that's
Okay.
exactly what's where this is going. So you I think you can basically guess, but and then the thing that you want to happen does happen. Um, okay, so the key consequence of this sort of Hodge algebra structure is that you can prove um, that your vertex algebra decomposes as a direct sum of representations of these Qs and Q daggers that live in these little quartets, which are drawn here. So you, along with singlets, so you have operators which are invariant under Q plus and Q minus, and which are not in the image of Q plus and Q minus, which are just invariant under all of the Qs and Q daggers. And then you have things that combine in these quartets. This is one way. I don't know if it's a very popular way, but this is one way to think about a lot of the consequences that you have in Hodge theory. And just a comment is that this exactly this quartet structure is something that you get from a more elaborate setting in the world of superconformal field theories. This is exactly the way that the multiplets of the four-dimensional superconformal algebra can recombine, um, whatever that means. But this structure is something that you expect from four-dimensional physics, but here it's derived entirely in the vertex algebra setting as a consequence of the positive definiteness um, of this Hermitian form and all the extra sort of gradings. Okay, so there are some consequences of this. Here's the first one. So it's probably a little bit fast, but it follows from that quartet picture that the cohomology of, say, the Q minus operator, uh, that would just be defined as kernel mod image in the usual way, is actually identified with the intersection of the kernels of Q plus and Q minus by things that are in the image of Q minus and Q plus. So this is sort of like a del bar lemma type of phenomenon. And a nice feature of this expression on the right-hand side is that it's manifestly invariant under this USP2 outer automorphism that exchanged Q1 and Q or Q plus and Q minus. So this means that not only so naively you had this construction where you had this family of differentials that you could use to define your semi-infinite cohomology, and you would necessarily get an isomorphic vertex algebra for any choice, but you didn't get an automorphism from that outer automorphism. But here you actually, because you can choose this representation on the right, you actually get you get an automorphism. So you get a natural USP2 outer automorphism whose cartan acts as the cohomological degree. So this USP2 is something that sort of mixes up things in different cohomological degrees. If everything's concentrated in cohomological degree 0, then it acts trivially. But in many interesting physical cases, you have stuff outside of degree 0, and then you get some sort of non-abelian mixing. And this is sort of like a Lefschetz SL2 action, as you would have in the Hudge theory case that mixes up different cohomological degrees. A further consequence that takes a bit more work, but essentially follows from this same identification, is that the semi-infinite cohomology itself inherits a graded unitary structure. So if this matter vertex algebra is graded unitary, then so is the BRST cohomology. So in particular, because these symplectic boson vertex algebras are graded unitary, this tells you that any so-called gauged symplectic boson vertex algebra, which is just a way of saying take symplectic bosons that admit a chiral moment map at the right level and take the BRST cohomology. Those things will all be graded unitary. And these are all the vertex algebras that come from Lagrangian field theories in 4 dimensions, as opposed to some more exotic non-Lagrangian stuff. Here's the formality morphisms. So this is what Jan, you were referring to. So I just drew this little roof here. So the result is that you have these maps and that they're quasi-isomorphisms. They're vertex algebra quasi-isomorphisms. So you can map. You can take the kernel of Q plus and induce a differential by the action of Q minus, and that embeds into your vertex algebra, your full vertex algebra with the Q minus differential. And you can also take the further Q plus cohomology, and after doing that, the induced Q minus differential acts as 0. And so this gives you sort of a roof of quasi-isomorphisms that relates the cohomology with 0 differential to your full, say, DG vertex algebra that you have when you have the full V with Q minus. And the derivation of this is just identical. I think this is what you were saying on just sort of the facts about having this set of algebraic operations and then getting this sort of quartet picture that follows from that. Then it's entirely formal, no pun intended, to follow the proof of Dillian Griffiths, Morgan, and Sullivan of the formality of compact Kähler manifolds. So this is what I mean by formality. I don't have a fancier meaning in some because I don't know how to situate any of these results in some sort of homotopy theoretic setting. What we mean by formality, for what it's worth, is this fact that you have a quasi or a roof of quasi-isomorphisms between the BRST cohomology and the full DG thing. A neat consequence of this is that if you're in this gauge symplectic boson setting, then by taking the semi-classical limit, passing to the associated graded, and then doing some additional sort of restrictions to certain graded subalgebras, by the time you take the associated graded, you have a lot of gradings around, and you can pick various sort of graded subalgebras of the commutative thing. And if you do that judiciously, then you can actually land on a finite type derived symplectic reduction of your original vector space by the complex group action. And the formality argument actually follows through. So you prove formality. Now this actually means something in some more sophisticated setting that's a bit above my pay grade. But you get an actual formality statement for certain derived symplectic reductions. Again, subject to some funny condition. This thing I've written here is the analog of this level minus twice the dual Coxeter number condition that appeared before. So if you have a vector space, which is a representation of some complex algebraic group G, semi-simple or reductive, and if you have this condition on the trace in the representation, comparing it to the adjoint, that's when this construction works. I don't know if it should be true in other cases. And finally, sort of piggybacking off of some of these formality ideas, Um, a neat consequence, which I claim from higher dimensional physics is sort of obvious, but really, I tried to prove it for a while without using these techniques, and I couldn't make any progress. Um, is that if you have a group G, which is actually a product of groups, so the corresponding Lie algebra is just the direct sum of the algebras G1 and G2. G1 and G2 should both be semi-simple in their own right. Then you can take the BRST cohomology with respect to G1 plus G2, um, and the corresponding differential will be a sum of differentials, one having to do with the G1 action and one having to do with the G2 action. And you could either take the semi-infinite cohomology with respect to Q plus minus all at once, or you could do an iterated cohomology where you take the cohomology with respect to Q1 and then Q2. And it's not obvious that those are going to be the same in general. You could imagine that there's some sort of spectral sequence that's supposed to eventually converge somewhere, but it could have some higher terms. Um, but again, you can use this graded unitarity structure in order to build explicit roofs of quasi-isomorphisms. Where here on the left, I have my vertex algebra with the full differential, and then up, down on the right, I have the twice iterated cohomology where I took the cohomology with respect to Q1 first and then with respect to Q2. And this, of course, generalizes to arbitrarily many simple factors. So there's no consequence of thinking about the order in which you're applying these semi-infinite cohomology functors. Um, and now this remark here applies to everything that I've said in this results section, which is that there's this weaker version I mentioned at the outset um, of graded unitarity, the weak graded unitarity, where the filtration is not required to be good. And that's something that comes up in these boundary vertex algebras for three-dimensional gauge theories. Then there's a little bit of an extra condition on the G action, but it holds for all of those three-dimensional constructions. And so you still get these sort of formality statements, as well as the outer automorphism. Um, okay, I'm approaching the end of my time, and I'm also approaching the end of my talk. So that was the main set of sort of structural results. Um, what's left is to talk about work with in the other two papers. So with Harshal, my student, and with Arash, Madalena, and Leonardo. Um, and this has to do with thinking beyond these gauge theories where you just have gauge symplectic bosons. So if you're in the club of people who know lots of physics lore about these four-dimensional n equals two superconformal field theories, then it's generally expected that there are lots of theories that are somewhat more mysterious in exactly how to define them, even at a physics level of definition. Um, but where the vertex algebras have been sort of convincingly argued to be various things that people recognize. So, for example, there are a series of theories which are believed to have associated vertex algebras, which are, as listed here, Virasoro minimal model vertex algebras. So those are Virasoro algebras with a central charge of the form written here. But the ones that show up in nature, as it were, seem to be only the ones where the central charge is C 2 comma P, as opposed to general Q comma P. Similarly, certain interesting fractional level Kac-Moody vertex algebras, the so-called Kac-Moody boundary admissible levels, seem to show up, as well as more general WN minimal models. Um, I won't narrate everything that's written here. It's certain families of these W algebras. This is a non-systematic sampling. There's much more exotic models that people have opinions about. And just to say that there's a lot of things out there that are supposed to be in this universe of, say, 4D vertex algebras, which don't seem to admit a presentation as gauge symplectic bosons. And for these, establishing graded unitarity mathematically is an open problem in all examples. Everything except for these gauge symplectic boson cases. Um, And I have to say we haven't really made much progress on doing that. Um, what we have done is observe that if you make assumptions which are technically perhaps quite strong, but physically seem very reasonable, you can use graded unitarity to put very strong constraints on, say, the central charge of a Virasoro algebra or the level of the Kac-Moody algebra. Um, you should have in mind just the analog of the program of saying, okay, which Virasoro vertex algebras are unitary in the usual sense. So you say, I know my vertex algebra is the Virasoro algebra. I would like to know which values of C amongst the CPQs uh, support a unitary structure. The answer is known from ages ago. It's when P is equal to Q plus one. And we'd like to be able to say similar things in the graded unitary case, also for current algebras, also for W algebras, etc. Um, so I'll sort of describe what it looks like to ask this question and what our approach has been to learning things. But all of the results are quite conditional on some strong assumptions. So you might say, suppose that the vertex algebra I'm interested in, I just happen to know that it is a Virasoro vertex algebra. That's the whole thing. So it's generated by some field that we'll call the stress tensor T that has the usual Virasoro OPE, and so its modes have the usual Virasoro commutation relations. Um, an immediate consequence of the non-degeneracy of the Hermitian form, or really of the requirement that you have a non-degenerate good filtration in order for it to be graded unitary, is that you have to be talking about the simple quotient version of the Virasoro vertex algebra. So you can't have some null states around that you haven't quotiented out. And then what we do is something like this. We say, okay, in principle, there's a choice of a conjugation and a choice of a non-degenerate good filtration, and then these things are supposed to be constrained by a bunch of positivity conditions. We're just going to assume what the filtration is. That's pretty suboptimal in terms of what one would like to do, but in practice, we actually have maybe through some mystical physics intuition some idea about what we think these filtrations are likely to look like in any example that might arise. So we'll assume that the qth filtered piece of my Virasoro vertex algebra is just things that you get by acting with less than or equal to q of the creation operators of your Virasoro algebra on the vacuum state. So that looks very similar to the sorts of things we had in the symplectic boson and symplectic fermion case, except now it's a little bit more of a meaningful filtration because of the sort of more interesting non-commutativity of the Virasoro algebra. And then if you buy the assumption, then you can ask, what do I know about norms? And you know Katz determinants. So people know how to compute the determinant of the Gram matrix of the bilinear form that was this parenthetical form that I mentioned before. And if you track all the definitions and you track this choice of filtration, then you can predict what the sign of the Katz determinant at any given level L would have to be if you had a graded unitary structure with that choice of filtration. So what I've written here is that there's some known Katz determinant formula that says at level L, the determinant of the Gram matrix is some product of linear factors which have zeros at the minimum model levels with some known exponents. I've just written them with symbols here, but the expression for these capital L sub L P slash Q expressions are known. And then the claim is if you track all the signs, that thing has to have a definite sign. If you were unitary, you would want that to be positive, but for graded unitary with the choice of with the choice of filtration, that thing is supposed to have a sign which is given by the expression on the right-hand side. It's -1 times the sum from P equals 0 to L of the dimension of the level of the conformal level L subspace with grade P with respect to this extra P grading. And there's a missing P. There should be a P to the right of that infinite summation in the exponent so that the combinatorial identity below is relevant. This is just some pesky combinatorics, but you can show that the sum over P and Q of the exponents in the Katz's determinant is the same as the sum appearing in the exponent on the right-hand side. And that means that in order to have the correct signs at each level L, then your value of the central charge C has to be such that for each level L, only an even number of the linear factors in that infinite sum are positive. If you ever have an odd number which are positive, then you'll have a disagreement of signs. And luckily, one has enough control over all of these factors to just check what sort of a condition that gives you. So it's a fact that C2, 2n plus 1 is less than C2, 2n minus 1. And at an even level, the Katz's determinant has the following form, where the most negative 0 is at C2, 2n plus 1. The next most negative 0 is at C2, 2n minus 1. And then all of the other zeros are to the right of there. And if you meditate on that statement for a second, then you realize that this sign rule I had above means that every interval between two comma odd values of central charges at some conformal level will lead to an inconsistent sign. Sorry, I just have the underline there. So the conclusion is, if you're willing to make this assumption about the form of the non-degenerate filtration, you rule out every possible value of the Virasoro central charge for a Virasoro vertex algebra, other than exactly the two comma odd minimal model levels. Those happen to be the levels that are known to show up, known in a physics sense, to show up in connection with certain exotic four-dimensional n equals 2 SCFTs. So at least conditioned on this assumed filtration, graded unitarity is giving you sort of as strong a result as you could hope. I'll probably sort of breeze through the next two parts because it's just saying that analogous things can be pursued for other choices of vertex algebras. So if you choose to assume that the underlying vertex algebra is just a Kac-Moody current algebra, then again, there's some assumption you could make for the filtration, which is technically a very strong assumption, but it also is reasonably well motivated by physics reasoning, though not, I wouldn't say sort of, there's no like physics proof of it. It's just a physics expectation. And again, you can go and analyze Katz's determinants and rule out for low ranks. So for SL2, you can rule out everything except the boundary admissible levels. For SL3, you can rule out everything except for the boundary admissible levels. For SO4, using this fairly crude Katz's determinant argument, you can rule out everything except for the boundary admissible levels, as well as some other levels which have not been witnessed in nature, as it were. But well, I would conjecture that only analyzing the signs of a bunch of norms at the level of a determinant is a pretty weak condition, and so one might hope that even in this sort of suboptimal approach, you might be able to get rid of those -4 plus 2 over p levels via some more granular version of this reasoning. And finally, I'll end on this last slide. I'll zoom out so you can, with a lot more work, you can do a similar analysis starting with some of the W algebras. And the punchline is that the template basically follows the same pattern, that you have to, or at least as far as we've been able to do with our limited creativity, you have to make some sort of motivated assumption about a filtration. But with reasonable assumptions, you then reproduce collections of vertex algebras as the only possibly allowed ones, which are the ones which happen to match the lists that are sort of out there in the physics literature. And so it does seem, I mean, the punchline of all of this is maybe that you could ask what percentage of the constraint there's some properties that a vertex algebra is supposed to have so that it came from a four-dimensional n equals 2 theory, you might say. And you could ask informally sort of what percentage of those constraints are encoded in graded unitarity. And it may be that in some sense it's quite a bit. but that's a very fluffy uh, sort of understanding. Um, I think that we haven't really found the right way to think about this structure in examples yet because of the fact that we haven't been able to establish this property for any vertex algebras other than um, the gate symplectic boson cases. So there's clearly some ideas that would need to be developed to do a better job than these sort of crude analyses, and that's something that hopefully will come eventually, um, but I don't know now. I will stop there. Thanks for listening.
Thank you very much. Are there any questions? So, by the way, in the end, you said that this graded unitarity captures kind of a lot of information for vertex operator algebras coming from 4D and equal to theories, but is it kind of, I mean, your hope is that it's necessary and sufficient, it just all vertex operator algebras coming from
Yeah, yeah.
4D, yeah, the,
I doubt it's necessary and sufficient per se. I mean, I'm really speculating at this point. I don't know the answer. Um, if speculating, I would imagine that one needs a way to. I think one will need a way to um, motivate these these stipulated filtrations from first principles better. And that I think
mhm.
is we're missing ideas. We don't know on any sort of like general four-dimensional physics grounds in a really sharp way how to say if you're looking at a Virasoro algebra that comes from four dimensions, the filtration has to be of such and such a form. Um, I could imagine there being a story there, but if I knew the story, I would tell it. I don't know it at the moment.
Yeah, and another, it's a sort of, you mentioned this sort of analogy between 3D and equal 4, uh, or jets, well, jets
Mhm.
in Higgs with values in Higgs branches. But suppose that I don't know if I'm interested in the representation theory, like for and you also mentioned this Tingoff
Yeah.
paper on short quantity. Okay, so of symplectic singularities. Now, for the resolution of symplectic singularity, there is this nice representation theory developed long ago, I think about 15 years ago by Kamnitzer, Webster, and others.
Yeah.
It's sort of analog of highest way. Okay. And in some sense, the structure, decomposition, and the union of symplectic leaves, it's crucial not only for the representation theory, but for symplectic duality, which is a mirror symmetry for 3D and equal 4. Now, how much of this can be used? I don't know if I'm interested in representation theory, I mean, graded unitary modules. Mm. Is there any geometry?
Uh, Not yet. So
Yeah.
I don't have I would say that where the hints I think the hints that exist about some geometric connections to the representation theory of these things. At the moment, those hints are really coming from a direction that doesn't, at least for now, have much interaction with these unitarity ideas. Um, so in the physics literature, and even I guess some in some examples, it's been made pretty rigorous. Um, there's been observations that for certain, say, like Kac-Moody vertex algebras that are known to come or known to come from four dimensions, um, there seems to be some there seems to be some connection between the um, between certain nice modules for these vertex algebras and the K-theoretic what you might call the K-theoretic Coulomb wrench of
Hmm.
these theories. Um,
Yeah.
the relevant papers are originally by Andy Kneitzke and Laura Fredrickson, and then there's been work by Wenbin Yan and Dan Xie and Peng Shan. Um, and they've used the phrase four-dimensional mirror symmetry in connection with these ideas. Um,
Mhm,
and
mhm.
I don't know, I think it's still, to me, quite an open question exactly how to understand the sorts of technical results that have come out there. One of the one of the tricky things is that the representation theory of these vertex algebras is often fairly complicated. So because these are generally not C2 cofinite um, vertex algebras, uh, they can start to have pretty wild looking um, module categories. I hope you used a phrase which is graded unitary module, which we haven't defined it yet, but but there should exist a good physically motivated definition of a graded unitary module for a graded unitary vertex algebra. And I certainly would hope that that will be a useful organizing principle on these module categories, which are otherwise a bit unwieldy. Um, but I don't have any claim to success yet. So
Okay.
maybe the answer to your question, your geometric question, is I can't answer it yet, but I think that it might be a thing to start thinking about after we've done more of the homework of um, of really working out the sort of formal properties of this graded unitarity in the module setting.
Okay. Good. More questions? Well, if there are no more questions, so Chris, thank you very much. So indeed, it's very interesting, inspiring talk. Thank you. But then
Thank
this is
you.
it for today. All right. Thank you. Thanks